Ladies and gentlemen, our next guest speaker has achieved breakthroughs that even in science fiction might sound a bit far-fetched. Plants endowed with the superpower to detect explosive and send off alerts. But the research he's speaking on today will be familiar with a big fan of the movie of James Cameron. Yes, the name of the movie that popped up in your head now, I'm talking about Avatar. James who marveled forests lighting up magically at night. The important difference is, rather than on the moon of Pandora in the year 2154, this professor is aiming to do this right here, right now on Earth, with the topic, how light-emitting plants work and its relevance to sustainability. Ladies and gentlemen, may I present to all of you, Professor Michael Stephen Strano.
Great, thank you very, very much. It really is my pleasure to be here. It's my honor. It's my first time speaking at the WATS Forum, and it's difficult actually to follow the former Prime Minister of Bhutan, who spoke to us about something far more important, which is human well-being, happiness, and flourishing. And if my wife is watching, I'm one of the men who filled out my survey that I'm happily married. I'm indicating that. But I thought what I would like to speak to you today. I've changed my title somewhat. I want to talk about using nanoscience to expand the role of living plants to help humanity. And this is an area of research that I started at MIT, and I'm very interested in getting feedback from the public about where we can go with this technology. But I thought I'd first introduce myself. I'm at the Massachusetts Institute of Technology. If you travel to the United States, we're on the East Coast, Cambridge. And I'm in the chemical engineering department. It's one of the oldest chemical engineering departments. And we have the first Ph.D. degree in chemical engineering. We work in a 30-60-90 triangle. So if you remember from geometry, we think a lot about shapes. And in the upper left-hand corner is the MIT dome. It's an iconic dome. And I think we're most widely known for our students who are very creative, and without which the work I'm going to tell you about would not be possible. In fact, our students are very creative. They often pull pranks on campus. Here's one where they actually put a police car on top of the MIT dome. This is not a photoshopped image. So if we don't keep our students busy, they'll pull pranks like this. They'll put a police car on top of the dome, and so part of my job as a professor is to keep them directed towards more creative endeavors. And this is my research team. I lead a team of about 25 people, and we study nanotechnology. And we work in the area of materials and medicine and energy. And more recently, we've started to direct our attention towards plants. And I'll explain that in a minute. But I thought I could give you a feel for my research and what we try to do by looking at some of our recent work, some of the recent headlines that we've garnered from the MIT press office. But whoops, before I do that, I wanted to explain nanoscience and engineering. A nanometer is, if you take a look at a human adult, the nanometer scale is where biological cells are constructed of proteins and lipids. You can think of the molecules that make up living things as being on the scale of the nanometer. And so as a scientist, I look at the nanometer scale. I try to understand phenomena there. And then I try to engineer materials that can interface at this level. So one of the ways to think about this is that in my lab, I can make building blocks at this small scale that I can swap out with nature's building blocks and try to get new functions. So we'll talk a little more about that. So I've done this. I've made my group has made a new wetsuit. If you use a wetsuit for water sports, we've made the warmest wetsuit in the water. We've lowered the thermal conductivity quite a bit, and it allows humans to go into Arctic temperature water without lack of survivability. So this new wetsuit is engineered. It's an example of the use of materials to create new technologies. And we've created in my lab, we've created cells that are essentially robotic. These are very small synthetic cells that are autonomous and can move around and sense things. They're the size of a human cell, but they're made to be electronic and autonomous, and we're applying them to different problems in the technology space. We're making materials out of these synthetic cells like we are made of biological cells. And we've invented a technology that can generate electricity from thermal fluctuations. In fact, at the top of that 36, 60, 90 triangle building, we have a device that can generate electricity from just the ambient temperature fluctuations. And so this is something that we're also working on. But what I want to talk about today is the use of plants as technology. It's a relatively new area for us to work in. Can we turn plants into sensors? Can we turn them into lights? And can we learn about plants and human-plant interactions using new technology? And so first, I want to start off with why plants. Plants haven't been considered the starting point for technology. So there have been very few engineers like myself to look at a plant as the starting point. But they have many advantages. You know that they harvest energy through photosynthesis, but they also store that energy as saccharides inside the plant itself. So they're a combination of a solar cell and a battery. They have access to water through transpiration. They're constantly drinking from the soil. And if you're a chemist, you know that flowing water, there's chemistry you can do with that. They're already adapted to harsh environments. So if you leave your cell phone outside, it's a challenge to keep it stable and working for a week, a month, a year. But plants are already adapted to the harsh environment. And they're adapted because they self-repair. So the things that humans make don't, as a rule, self-repair, but plants have this built-in mechanism to self-repair. I say they're doubly carbon negative because they're made of carbon dioxide through carbon fixation, but they also store their energy as also from carbon dioxide, and they're very easy to recycle. Okay, so what I want to talk about today, we'll talk about some work where we've made a plant that can produce its own light from its own stored chemical energy that it makes from photosynthesis. We'll talk about modifying plants using nanoparticles to give them new functions. We'll talk about can a plant be a sensor? Can it detect things in the environment, and can we get that information that it collects into our cell phone and into the human world? And on a related note, can we use the information that plants collect that's important to them and get that, like for example, drought? Can we get that information into the human world where we can act to help plants? So let me go ahead and get started. So this is a video that talks about our work to create a light-emitting plant. So this is a plant that we've used nanotechnology techniques to turn some of its stored chemical energy into light emission.
By embedding specialized nanoparticles into the leaves of watercress plants, MIT engineers have been able to induce the plants to give off a dim light for nearly 4 hours. And they believe that with further optimization, such plants will one day be bright enough to illuminate an entire workspace. Imagine that instead of switching on a lamp when it gets dark, you could read by the light of a glowing plant on your desk. To create their glowing plants, the MIT team turned to luciferase, the enzyme that gives fireflies their glow. Luciferase acts on a molecule called luciferin, causing it to emit light. Another molecule called coenzyme A helps the process along by removing a reaction byproduct that can inhibit luciferase activity. The MIT team packaged each of these 3 components into nanoparticle carriers of varying size to help each component get to the right part of the plant. To get the particles into the plant leaves, the researchers first suspended the particles into a solution. Then, plants were immersed in the solution and exposed to high pressure, allowing the particles to enter the leaves through tiny pores called stomata. Once in the leaves, the particles gradually release luciferin, which then enters the plant cells, where the luciferase performs the chemical reaction that makes luciferin glow.
So this is an active area of engineering and scientific research in my lab at MIT. This is my one scientific slide. It's meant for those that want to know how this works. So there are 3 kinds of nanoparticles shown. One is made of a polymer called PLGA. It's commonly used in drug delivery. It's used in a lot of medicines. Another particle is made of chitosan, which is essentially crab shell, and then a third is made of silica, like small sand particles. But these 3 particles interface with the plant to turn its own stored chemical energy into light. On this next slide, I have perhaps the engineer's view of a leaf. It's just a rectangle. So this rectangle shows the leaf. These 3 particles go through the pores called the stomata, as the video said, and some of the particles are designed to go into the plant cell, and the other particles are designed to stay in the vasculature. But all of them chemically interact biochemically with the plant to turn its stored chemical energy into light. And we publish this in the scientific literature. Okay, and the reason why we're able to do this is because for the first time we've made some breakthroughs at MIT on how to get small particles into living plants. So we actually have a theory, and it seems to work very well. We can design particles that can reach the deepest recesses of the living plant. So for the first time, we can hack the plant, and we can put particles into it that can chemically interact with it. Okay, that leads to the question why? Why do we want to make a light-emitting plant? So this idea has been with humans for quite a bit, as I'll show. You'll see popular artist conceptions. This is actually there's been a long-standing idea of making trees along a road that could be that could illuminate and take the place of street lamps. They would not need to be plugged in. They could provide lighting, and of course, as my introduction said, we've seen in popular culture, like the movie Avatar, we've seen depictions on an alien world of light-emitting plants. So I actually asked my children if they could tell me the story, some children's story or nursery rhyme, the oldest one that refers to a light-emitting plant. And actually my 9-year-old at the time, Grace, reminded me that in the Epic of Gilgamesh, there's actually a reference to the light-emitting plant. So I thought that was interesting. Let me skip through that. Yeah, so in the Epic of Gilgamesh, 2100, there is so it's the oldest surviving work of literature. It's one of the first stories that humans wrote down. On the 11th tablet, Gilgamesh is told the location of a glowing plant that's in the bottom of the ocean, and the plant actually holds the secret of eternal life, and it's actually a box rose. And Gilgamesh dives down and has to bring this plant up. And in a very unselfish act, which is uncharacteristic of Gilgamesh, he proposes to give this plant to the elders of the community so that their knowledge can be preserved. So this idea has been around quite a bit. I was in the National Museum of Singapore, and if you look, whoops, see if we can do this here. Yep. And they have an exhibit which is actually glowing, falling parts of plants and petals, and they have depictions of light-emitting plants in this exhibit. So once you see that, this has been a part of our popular culture and maybe a part of human endeavor for, as you can see, literally thousands of years, right? Okay. However, we're treating it like a very serious engineering project, not an aesthetic project, but we're treating this the way that we would to design a better light bulb, right? In that this is the one slide where I have data. On the y-axis is photons per second. It's how bright the plant is, and on the x-axis is its duration. So we collect a lot of data that look like this, and you see that there's a trade-off between the duration and the brightness. And so we do experiment after experiment, and we're slowly making the plant brighter and making it last longer. And in fact, here's that same plot, brightness versus duration, and you can see these are different recipes, if you will, and you see that we're mapping this space, getting to longer and longer time. And this brings up the question of how long. What's the maximum possible? And what I can report is, if you take our current numbers in blue, if you look at what's theoretically possible, it's these series of 3 lines based on different assumptions. But you can see that we can at least be an order of magnitude greater in brightness and in duration. And so we're actively working to do so. Okay, so I want to switch gears and talk about plants as chemical sensors. And this is an area where we can engineer plant-human communication. And so this is, a few years ago, we published a paper where we turned a spinach plant into a chemical sensor that can look for, among all things, explosives in the soil. So this is actually a spinach plant that will send an infrared signal to your cell phone and tell you if it detected something in the soil. So this was, and it did so by using 2 types of nanosensors inside the leaf. So I'll show you this in the video here. This is a spinach plant where we've wrapped the roots in cheesecloth. And if you take a small amount of picric acid in water and you put that into the water that's feeding the plant, then as the plant transpires, as it brings up this water through its roots and through the stem and into the leaves, we can use 2 different nanoparticles. One will send an infrared signal, and you can pick this up with essentially your cell phone. So this is a cell phone camera, and you can see here that on the right, you're getting a modulation as the plant detects the explosive. On the left is a reference, and it can send that, and it can bring this information into the real world. And so into the digital world where you can, and so this idea of plant-human communication opens up doors to where we can tap information that the plant collects and bring it into the digital world. So we've explored this, and we've also started to turn sensors inward. Another idea is to use the internal signaling inside plants themselves and bring that information into the digital world. Here I show a different sensor where every time, so when a plant is wounded, it sends a chemical signal all throughout the plant to warn and to activate its defenses. So here we have, being brought to a cell phone, we have every time this caterpillar bites this living plant, every time it bites, that information is brought to your cell phone. And so this idea that we can have plants monitor the environment, they can monitor themselves and use information that they collect themselves and bring it into the digital world is one that I think is worth exploring. And that brings me to my last topic. You know, when you look at a plant, you might see a static device. In fact, you could fool yourself into thinking that it's an inanimate object. But plants actually are very dynamic and moving. And one of the ways in which they move is through these pores called the stomata. Some stomata like this open and close like a switch. And so we asked the question, could we make an electrical circuit across that pore and have the plant open and close and flick a switch like we do with so many of our appliances? And this had never been done before, so we made a simple applicator, and it makes a small conducting pad, and it can transduce this opening and closing of the stomata. So I have that here in this video.
Chances are you've never had a conversation with this peace lily, but if it could talk, what would it say? Water me. MIT engineers have invented a sensor printed on a plant's leaf that allows plants to tell owners when they need water or if they've had too much.
What we've invented is a sensor that can electronically wire up a pore that's found on the surface of most leaves called the stomata. And by turning the opening and closing of this pore into an electrical signal, we can monitor the plant and how it uses water and predict drought in a way that we weren't able to do before. And it's the first example of using a micro and nanotechnology to bring this information that the plant has into the electronic world.
The line in between these two holes is positioned exactly on top of one of the stomata. And once we inject the ink will be printed exactly on top of the stomata. So this is already the printed pattern, and it's already been aligned and dried out on top of the stomata. This is the sensor ready to use. So now we will attach these copper wires to the printed ink so that it has good contact with the printed conductive ink.
These stomata pores look a lot like a human eye. They open and they close. When they open, water evaporates from a layer inside the leaf. When they close, it turns off that evaporation. As the plant undergoes a greater and greater extent of water stress, the opening and closing will become slower and slower. You can think of the plant as becoming drowsy. But if you can measure that with precision, it's a very good early detector of oncoming drought. You can detect the onset of this water stress long before the tissue starts to be harmed. So you can save the plant.
According to the World Bank, droughts wipe out enough produce to feed 81 million people every day for a year, equivalent to the population of Germany.
Ultimately, strategies like this could allow us to plant crops that are more and more sensitive to drought, but we're able to mitigate it so we can increase food supply.
Strano and his team are working on a way to make it easier for people to use and apply these sensors with a sticker. By placing a sticker on the plant's surface, the owner of the plant can read the plant's information wirelessly on his or her phone.
Okay, and so one of the things that I appreciate about being here at the WATS Forum is that we get to start, we can bring these ideas to the public and start the discussion about how they can best help human beings. And so I've partnered with Sheila Kennedy in the Department of Architecture at MIT, and she has been thinking about designs around the light-emitting plant, the designs around human infrastructure, dwellings, and how to funnel light and water into buildings in a sustainable way that could foster plant-based lighting. And so this is actually an exhibit at the Smithsonian Museum of Design. If you're traveling to New York City before the fall, there's currently an exhibit there. You can see the light-emitting plant on display, and you can see this exhibit. And what Sheila has done, I think is remarkable. She has envisioned how humans can interact with plants. Here they're maintaining the water infrastructure to maintain lighting, and also how plants can illuminate and how they can impact human social interactions. And so with that, I am out of time, but I do want to say I actually part of my work, we're taking these technologies and we are directing them to agriculture. So as the last video showed, so I have a satellite lab in Singapore where we're particularly trying to make technologies to help urban farming. So it's called DSTAP, or Disruptive and Sustainable Technologies for Agricultural Precision. However, I want to make special thanks to MQDC for funding, particularly the sustainable and plant-based lighting effort. We could not have gotten this far without them, and I would like to thank all of the audience also for your attention. Thank you.
Thank you very much, Professor Michael Steven Strano. They are so beautiful. You agree with me? All of the plants and the flowers, especially the color in the dark